Hi everyone, and welcome to this new Hurricane tutorial. Today we are going to learn how to create a basic emission step by step, and what better way to start than with the sound preset. To get started, we will use a simple plane in our Blender scene and assign it the sound preset. The great thing about using presets is that Hurricane automatically adjusts almost all parameters for you to get awesome sound behavior right from the start. In the emitter solver module, we can see that the solver type automatically assigned is PBD, which is ideal for sound simulations. The first step we must take is to go to the simulation module and increase the max substeps to at least 10. If we play our simulation, we can see that everything works correctly. Next, we'll lower the resolution value to achieve a higher density and emit a greater number of particles. We clear the cache and play again. You'll notice that by default, the sound preset enables the BeFX exclusion toggle. This feature prevents new particles from spawning on top of existing ones, ensuring a clean stream. If we disable it to compare, we can see the particles crowding aggressively at the spawn area, creating a chaotic emission. Keep in mind that with BeFX exclusion active, the actual number of emitted particles may differ slightly from the theoretical count. Now, we might spot a small detail. The particles seem to move slightly erratically, showing minor jittering. We can easily solve this in the emitter solver module by adjusting the stiffness value. Stiffness regulates the repelling force between the particles themselves. While in cloth simulations, a higher value is preferred to help prevent particle overlap and fabric self-intersection, in some simulations, lowering to a very low value, such as 0.05, prevents excessive interparticle repulsion and allows the sound to settle smoothly and stably. We replay our simulation, and we can now see how the particles settle and behave correctly among themselves. Let's increase particle density even further to test a super useful feature called sleep. With sleep, we can define specific conditions for particles to go to sleep. Based on a minimum lifespan and velocity threshold, particles freeze, removing all movement while keeping their collision active. This allows the sand to pile up stably, forming a mountain without collapsing. To clearly visualize this effect, we go to the display module and enable preview mode. This will show us, through particle coloring, the different states they transition through: awake, ready to sleep, and fully asleep. We can observe how, in a visually striking way, the particles progressively accumulate to form a perfectly stable mountain. We can return to the solver module and increase the sleep delay value. This parameter ensures that particles won't go to sleep until their lifespan reaches at least the specified number of seconds. If we notice that some particles fail to go to sleep or exhibit slightly erratic behavior, we can slightly increase the substeps to fix it. Additionally, in PBD simulations, it's always very useful to work with the Velclamp parameter to limit maximum particle velocities and maintain full control over the simulation. We have many more tools to enrich our sound simulations. For example, the attraction attribute, which groups particles into clusters to achieve wet sand or even snow effects, as well as friction controls. We will explore all these options in detail further ahead. Now let's move to the next preset, Flow Liquid. As its name suggests, this preset will generate a continuous stream of fluid. In this scene, we will have a sphere acting as our emitter and the torus functioning as a collider to add more dynamic interaction to our simulation. We select our sphere and assign it an emitter using the Flow Liquid preset. If we hit play, you'll notice the initial result isn't entirely satisfactory. as we will still need to tune a few key settings to adapt the behavior to the specific emitter type we've added. First, we slightly reduce the particle size. This helps them to concentrate better around the emission point without over-dispersing. With just this adjustment, we achieve a much more consistent fluid stream. Next, we add the torus as a collider and slightly tweak the floor's friction value. We play the simulation again, and now we can observe a far superior, much more realistic fluid behavior. In the simulation module, we check the substeps. Depending on the type of simulation we are running and the speed of our particles, keeping substeps at a value of 5 is sufficient. However, if we were to increase the emitter speed or particle density, it would be advisable to raise the substeps to ensure greater control over the fluid's behavior. We increase particle density by lowering the resolution value to achieve a richer, more detailed result. In the solver module, we have fluid dynamics section to shape our fluid behavior. Parameters like pressure, rest density or near, which controls short-range repulsion forces to adjust surface tension, allows us to define its cohesion. In this example, by lowering the near value, particles stay more tightly grouped, producing a much smoother flow. As we can see, the results now perfectly matches what we are aiming for. Now let's increase the simulation density even further to achieve a much higher level of detail. We observe that with 5 substeps, we still maintain an excellent result. So we will simply fine-tune the colliders to our liking and let the cache finish baking. Once the calculation is finished, we replay our simulation and will notice that small isolated particles are violently ejected in certain areas. It's not strictly necessary to fix this, as when we generate the final mesh, we can easily filter out those stray particles so they don't appear in the final geometry. We go to the surface module and select the liquid meshing option to generate our mesh. This mesh is generated by default with standard values. But since the final look depends entirely on the scale and level of detail of the simulation, it will always be necessary to tweak a few settings to fit our scene. We have two resolution modes. Preview, which allows us to work smoothly and comfortably with the mesh, ideal for generating foam or previewing the fluid without overloading the viewport, and Render, where we can configure our high-quality final settings for rendering. We can hide the mesh visualization or enable particle display at any time. Generally, when configuring the mesh, I like to keep both active in the viewport to ensure the mesh matches the actual particle silhouette as closely as possible. We adjust the resolution and mesh size to achieve the best possible definition. Here we can spot the issue with loose particles, which create unwanted tiny floating droplets in the final simulation. To solve this, we have the Area Threshold tool, which removes those isolated particle zones from the mesh. Finally, we can increase the mesh smoothing if we deem it's necessary, though with caution. If we overdo it, we will lose important details of the liquid surface that we might want to keep. We can go to our display module and select any of the available visualization modes, or even create our own custom color maps to later use these colors as attributes within our shader. In this section, we'll take a look at how the geometry liquid presets works. For this setup, we'll use a container acting like a pool where our fluid will fall. As usual, we select our mesh, assign it as an emitter, and apply the geometry liquid preset. This will generate a particle grid where we can precisely define both size and resolution. Next, we will select the mesh that will act as our collider and add it to the system. Personally, I usually hide the collider visualization to focus exclusively on the particle simulation. We clear the cache just in case and hit play. We can see that the initial simulation is quite low resolution and rough. but the base behavior works correctly. We go to the emitter section inside the particles module and lower the resolution value to increase particle density. We clear the cache once again and play the simulation. We immediately notice that the emitter seems to inflate. This happens because by default, Geometry Liquid sets a particle radius of 2.0 to maintain volume properly when the fluid is enclosed in a container. Lowering this particle radius to 1.5 gives us a much better and more natural result. We observe how the particle impact generates a bit of vorticity, causing some particles to shoot off out of control. To minimize the issue, we increase the substeps. The result is now much more stable, preventing particles from flying off chaotically. We notice a slight initial wave action, but the fluid calms down very quickly. This is a classic behavior in SPH or PBD solvers. To enhance the result, we enable the Vorticity Burst tool. This feature injects extra inertia into the particles, creating a much more dynamic and visually striking fluid motion. We specify the duration of the vorticity in frames, its decay time, the impulse force, and the axis affected by the extra inertia. We clear the cache and play to observe the results. We can appreciate how the fluid now exhibits much more detail and a far richer wave motion, delivering a significantly more interesting result. Finally, just as before, we generate the mesh. We tweak our settings to achieve geometry that faithfully conforms to the actual volume of our particles. Later on, in the future tutorials, we will explore in detail how the foam, bubbles, and spray system work. Let's move on to the next preset, cloth. Now, we'll see how cloth simulation generation works in Hurricane. In this scene, we have an object, the matte ball from MathPlus, acting as our collider, and the plane functioning as our cloth. We add the matte ball as a collider and slightly tune its friction and damping values. Before assigning the emitter, it is essential to ensure that our mesh has good geometric resolution or subdivision count, as this will determine the level of detail and faults with which the cloth can wrinkle. Once the resolution is verified, we select the plane, assign it as an emitter, and choose the cloth preset. As always, Hurricane will automatically configure the solver with optimal settings for cloth simulation. Next, we play the simulation and we can already observe a highly satisfactory initial result. It is important to clarify that in Hurricane, we always work initially at the particle level. Although we can generate the geometric mesh at any time, once an initial simulation has been baked to provide deformation data, it is far faster and smoother to tune the scene directly using particles. Additionally, the workflow is much cleaner if we hide the emission visualization. Next, we generate the mesh to preview the final cloth surface. We can increase the mesh subdivisions to achieve a higher level of detail in the final result. Remember to apply this change to the render resolution as well. Now, let's move on to the constraints module. This is where we can attach constraints to any of our emitters. By default, when using the cloth preset, cloth constraints are automatically generated on our emitter. We have four main control types in our cloth constraints: stretch, shear, bending, and compression. We will explore these controls in detail later, but for now, we'll simply tweak a few values to observe the different behaviors. First, let's enable constraint visualization to understand exactly what each parameter controls. We hide the mesh display and enable constraint rendering. Upon playback, we can observe a network of lines interconnecting the geometry. These lines act like tiny rubber bands holding vertices together. We can toggle individual visualization for each cloth constraint type to inspect them separately with greater clarity. Let's go back to working with the mesh display. When re-enabling it, it might not show up immediately in the viewport if we have tweaked constraint values, as the mesh needs to refresh its structure. To fix this, we simply click the Update icon, Update Mesh, to regenerate it. Stretch creates links along the main edges of the mesh to resist elongation. Shear adds diagonal connections across quad faces to resist angular distortion. And bending links more distant vertices across adjacent faces to control fold stiffness and bending resistance. Meanwhile, compression governs the response when vertices are pushed closer than their original rest length, preventing the fabric from collapsing or wrinkling chaotically. Within the Constraints Visualization section, we can enable various display modes to evaluate the internal state of the constraints, analyzing parameters like tension, compression, or elongation levels across the fabric in real time. We can adjust settings like thickness or display ranges to achieve a much clearer graphical reading. This tool proves immensely useful for diagnosing cloth behavior and obtaining immediate visual feedback while tuning our constraints. Now let's lower the bending and compression values on our constraints to achieve more flexible and pliable behavior, allowing many more detailed folds and wrinkles to form across our cloth. We can observe that the cloth adopts a fluidity almost identical to silk, smoothly conforming to the surface and falling into the collider's crevices thanks to the flexibility of its constraints. In future tutorials, we will dive into even more advanced cloth controls, exploring how to create complete garments and simulate clothing comprehensively. Let's move on to the Softbody preset, the final one in this introductory series, leaving snow to be explored in detail in a dedicated tutorial. In this scene we have Suzanne, the Math Plus version, which we'll use to create a Softbody simulation. As you can see, it features high-density geometry that, as you well know, would be practically impossible to simulate smoothly using Blender native tools. We select Suzanne, add it as an emitter, and apply the Softbody preset. As usual, Hurricane automatically configures the solver with the ideal settings for Softbody behavior. We observe how a grid pattern is generated. This architecture represents an enormously powerful tool. Conventionally, the point mode is used, where a point is located at each vertex of the mesh, which is simple but limited. Operating through a three-dimensional grid is technically much more advanced, allowing geometries of extreme densities and structural complexity to be deformed with absolute precision and stability. We set a balanced grid density, neither too high nor overly low, allowing the geometry to deform with sufficient flexibility without generating an excessive number of constraints that would slow down computation. Once resolution is configured, we hide the emitter and play the simulation. We immediately notice that the initial result is far from ideal. Particle interpenetration occurs and the object bounces continuously. The primary requirement is to increase the substeps, an essential step for any softbody simulation to guarantee collision stability. Additionally, we'll increase constraint iteration to resolve elasticity with maximum precision. We play the simulation again and observe a significantly superior and far more stable result. Before tuning our constraints, we'll generate the mesh for our softbody to evaluate its deformation. Once generated, we hide the particle emitter to focus exclusively on the mesh surface. We can already appreciate how the object deforms, though we notice a small localized pinch or crevice on the bottom area. We can mitigate this detail by enabling Mesh Smooth, but the ideal approach is to address the structural behavior directly through constraints. By tweaking tension and compression values, we can achieve vastly different mechanical responses, ranging from rigid rubber to highly malleable bodies. By setting compression to 0 and keeping tension low, the mesh adopts an extremely soft consistency, behaving just like jelly. If we are aiming for ultra-faithful soft body behavior, deforming upon impact but returning accurately to its original volume and geometry, we enable shape matching. Although these calculations add a slight computation overhead, it guarantees an impeccable result. Enabling shape matching alters constraint sensitivity, requiring more contrasting or extreme values to tune elastically. To demonstrate this, we fix tension at 0.1 and compression at 0, toggling shape matching on and off to observe the stark contrast in mesh response. With shape matching enabled, we reduce tension to 0.01. We can observe how the mesh undergoes far greater deformation upon impact, while still restoring its original geometry cleanly and flawlessly. Finally, we return to the emitter to change the emission type. Instead of geometry mode, we select interval mode. This method allows us to spawn multiple softbodies sequentially over time. In this example, we configure emission to spawn a new softbody every 20 frames, up to a maximum limit of 5. We can observe how they interact and collide seamlessly with one another on this occasion. If any misalignment were to occur in other scenarios, we have various dedicated tools to resolve it, which we will explore in detail in the future tutorials. That's all for today's tutorial. Later on, we'll create specific tutorials dedicated to snow simulation. But on this occasion, we wanted to introduce you to the essential tools for generating the most common types of effects. The demo scene with all emitters is ready for download on the official BeFX Studios website. See you in the next tutorial!